Okay, hi everyone. Welcome to this talk. So we are super delighted to be able to welcome Noam Brown from OpenAI here with us today. He's been responsible for multiple of the biggest developments in AI game playing over the past few years. He created the first AI systems that could beat the top human players in poker, which was recognized by Science as one of the top scientific breakthroughs in 2019. And for this work, he was also awarded the Marvin Minsky Medal for outstanding achievements in AI and named as one of the MIT Tech Review's 35 Innovators Under 35. More recently, he's also developed Cicero, the first AI system to achieve human-level performance in the natural language strategy game of diplomacy. So super excited to hear about what you have to share with us today.
Okay, thank you. Oh, I think I'm mic'd up, yeah. Okay, hi everybody. My name is Noam. I want to start off by giving some motivation and talking about when I started working in AI as a grad student. So I started grad school in 2012, and I was working on AI for poker basically from the start. And around the time I started, people had already been working on AI for poker for several years. And at the time, it was felt like the system had been figured out, and it was really just a matter of scaling the models further. I have this plot here showing, each year and roughly the number of parameters, or proportional to the number of parameters that was in the model each year that we trained. So every year we would train this model. All the other research labs would also train models that played AI, and we would all get together every year and play them against each other in this thing called the annual computer poker competition. And yeah, every year we used roughly the same algorithm, but there was a lot of challenges in scaling it. We had to make it more distributed, train it on for longer, on more compute, and every year the models would get better, and every year they would beat the previous year's models. And in 2014, my advisor and I developed an AI that beat all the other bots in the annual computer poker competition. We got first place. And we decided to try to play it against actual human experts. And so this led to the 2015 Brains versus AI poker competition, where we challenged 4 top poker professionals to an 80,000-hand poker competition. We had $120,000 in prize money to incentivize them to play their best. And ultimately, our bot, Cloutico, lost by a pretty sizable margin. So the amount was 9.1 big blinds per 100. If you're not familiar with poker, that doesn't really mean much. But basically, it was a substantial loss. It wasn't like a crushing defeat, but it was a pretty substantial loss. And during this competition, I noticed something interesting. You see, our bot had trained on roughly 1 trillion hands of poker leading up to this competition. It had been playing poker nonstop on thousands of CPUs for months leading up to this competition. But when it came time to actually play against these experts, it acted almost instantly. It would take about 30 milliseconds or so whatever it took to just look up the policy for whatever state it was in and just act instantly. The humans, meanwhile, if they were in a very difficult spot, they would sit there and they would think. And they would sometimes think for 5 seconds. They would sometimes think for 5 minutes. But if it was a difficult situation, they would take the time to think through what to do. And it occurred to me that maybe this is what is missing from our bot. So after the competition, I decided to look into this direction and see how much of a difference does this actually make if we add this capability. And this is what I found. This data is from a paper that I published in 2017 with my advisor. So the blue line is if we don't do any search or planning. If we just do what we had been doing for years at that point, just training bigger and bigger models, but having them act instantly when it came time to actually play. The x-axis here is the number of buckets. This was before neural nets were really taking off, and so we used k-means clustering. But basically, it's the number of parameters in our model. And it's the number of parameters in our model times some constant factor that we won't go into, but basically roughly proportional to the number of parameters in our model. And the y-axis is distance from Nash equilibrium. So the lower this number is, the better you are at poker. I'm not going to go into a lot of details about this because I don't want to make this a poker talk, but the lower that number is, the better you're going to do when it comes time to actually play poker. And you can see that indeed, as we scale up the model, it was getting better at poker. The distance from Nash equilibrium dropped from around 800 to around 400 as we scaled up the model 100x. The orange line is the same model if we add search. If we add the ability of the model to think for about 30 seconds before acting in the final round of the game of poker. And you can see, even for the same size model, you're getting about a 7x reduction in distance from Nash. To me, this was staggering. I had been working on AI for poker in grad school for about 3 or 4 years at this point. And over those 3 or 4 years, I had managed to scale up the models by about 100-fold. And I was really proud of that. That was, I thought, really impressive work. And here, if you were to extend this blue line out and see how far would you have to extend it to match the performance that you're getting by adding search, the answer would be 100,000x. And so just by adding search, we were able to do the equivalent of scaling the models by 100,000x when it took me 3 years to scale it by 100x. So at this point, I realized everything I had done in my PhD up until this point was going to be a footnote compared to just adding search. Based on this result, we changed our approach completely. The focus became, how do we scale up search? And in 2017, we did another competition with 4 top professional poker players. This time, we played 120,000 hands of poker with $200,000 in prize money to incentivize the players to play their best. And the bot ultimately won by 15 big blinds per 100, whereas previously the previous bot in 2015 had lost by 9 big blinds per 100. And each human lost individually to the bot. This was a very surprising result to everybody. It was a huge surprise to the poker community. It was a huge surprise to the AI community. It was even a huge surprise to us. We were not expecting to win by this kind of margin. And in fact, I think what really illustrates this is that when we announced the competition, there emerged, not surprisingly among the poker community, a very active betting market on who would win. And the odds against us were about 4 to 1. And even after the first 3 days of the competition, when we had won for 3 straight days, it was still a 50-50 in the betting markets on who would win. But by around the 8th day, it became very clear that we were going to win. And the only betting market that remained was which human would lose the least by the end of the competition. We followed this up in 2019. I continued in this direction of how do you do search and planning in the domain of poker. And in 2019, we made a 6-player poker bot. The previous bot was just 2-player poker. Now we have 6-player no-limit Texas Hold'em poker. We played against, in 6-player poker with 5 humans at the table and 1 bot, 10,000 hands over 12 days. We used variance reduction techniques to reduce the luck factor. And again, the bot won with statistical significance. What's really interesting about this bot is that it cost under $150, the equivalent of under $150 to train, if you were to train it on cloud computing resources. And it runs on 28 CPU cores at test time. Now, the fact that this costs less than $150 to train means that we could have done this back in the 90s even, if we had taken the right approach. OK, so this was a big motivating factor for a lot of my future research in AI, this focus on planning. And I think looking back, it's really easy now to say, well, why didn't people work on planning in poker before? I mean, clearly it was such a huge win. And I think it's really hard to put yourself in the mindset of, everything's obvious in retrospect. But at the time, it was not obvious that this would work so well. And so I think there were a few reasons why search and planning was not as active a research area in AI for poker. And I think it has a lot of lessons for how people approach research in general and today. So, OK, why wasn't search prioritized in AI for poker before? And the first thing I should say is that people were working on search in poker. It just wasn't given the same emphasis that I think it deserved. And it wasn't considered the highest priority. And by the way, when I say search, I use it interchangeably with planning. I consider search a kind of planning. But basically, the idea is that the model is taking a longer time to act than its pre-computed policy would do. OK, so why wasn't it valued highly before? I think one thing was cultural factors. Researchers, especially in game theory, wanted to compute an equilibrium. And if you want to, you have to verify that you have an equilibrium. And so you want to have the entire solution up front. And if you're doing planning, then that means that you don't have the entire solution up front. And so you can't compute exactly how far away you are from equilibrium. And so this was kind of a cultural factor that the community came out of the community working on AI for poker came out of game theory. And so they had this bias against anything that wasn't computing the entire policy. Another is just the difficulty of doing experiments with planning. So as you scale up the amount of compute that's used at test time, it makes it very difficult to measure how well you're doing. It makes experiments much more difficult, especially in a game like poker where you have such high variance and you have to play maybe 1 million hands of poker between 2 bots in order to tell which one is better. Having the model take 30 seconds per hand, it just makes things very difficult. Another was incentives. And I think this is especially true for academic researchers today to pay attention to. People were always thinking about, like I mentioned, there was this thing called the annual computer poker competition, and everybody was always focused on winning the annual computer poker competition, this kind of short-term objective. And the annual computer poker competition limited the amount of test time compute that you could use to 2 CPU cores. And the reason for this is just the funding that the organization had. It was very expensive to run these bots for millions of hands against each other if they were taking so many resources at test time. And so people were focused very much on this short-term goal of winning the annual computer poker competition at the expense of developing techniques that might work in the more important benchmark of beating top humans. And finally, I think the most important factor is that people simply underestimated the difference that it would make. If you had asked me before I did research on this direction, how much of a difference would it make if you added, if you figured out how to do planning and added it to the poker bots, I would say, yeah, maybe it's the equivalent of scaling up the models by 10x, which is a lot. I would not have thought it would be 100,000x. And I think that's a general trend that I've seen, that people underestimate just how much of a difference planning makes for these models. OK, before I go on to other games, is any questions about poker and planning? Yep.
Could you say a little bit about what search is in the poker process?
I can't. I don't want to spend too much time on it because I think one of the points that I want to make is that if you look at how search is being done at all these different games, it's very specific to the game. And when you go to a different domain, it's not necessarily useful for those other domains. But I think there is a general trend here that figuring out how to do search ends up being very useful. And if we can develop a very general way of doing search, then that has the potential for being very, very useful. To answer your question for poker, we would do these equilibrium computations that are these iterative algorithms. So it starts by playing randomly, and then it gradually converges towards an equilibrium. So in rock, paper, scissors, for example, this would be randomizing equally between rock, paper, and scissors so that you're guaranteed to not lose an expectation. Obviously, in a more complicated game like poker, the strategy is much more complicated. And so even if you're playing what would appear to be a defensive strategy where you're guaranteeing you could not lose, you actually end up winning in practice because the other player makes mistakes. Now, previously, all of this equilibrium computation was being done ahead of time. And what we developed was a technique that would allow us to better approximate the equilibrium by doing this iterative process more, but only for a piece of the game. So kind of like in chess, when you're at a particular board state, you only have to search through the possibilities that could come after that board state. We developed a technique in poker where you could compute an equilibrium for the possible states that could come after the situation that you're in, and not worry about the other states that came before or that are not possible to reach at the given point that you're in. Yep. Mm-hmm. Jamie?
So, forgive me, I know nothing about poker. I managed to make my way out of CMU not knowing anything about poker. But what you just suggested, was there a time space trade-off also, right? Because like computing an equilibrium and like storing it in a lookup table is presumably gargantuan, right? Whereas like doing search conditioned on like, you know, this many steps in a game, like you could imagine you're searching a much smaller space rather than storing the entire thing. Is there some trade-off that you see there also in terms of like, you know, the amount of total compute and the amount of things you have to store, or?
Yeah, that's a good point. And this was certainly a factor for, you know, when we were doing research on poker, I remember like we'd spent a lot of time figuring out how do we compress the representation of the strategies that, you know, we can store in as little space as possible. We'd have to use like all sorts of clever tricks to like, you know, for most of the game, we actually just had like a binary representation of like, do you raise or do you fold, and not worry about the probabilities so much. That, I wouldn't say that was the bottleneck for performance, but it certainly was a factor. And one of the nice things about doing search and planning is that like in poker, we no longer had to have a fine-grained representation of the strategy at the later rounds. Yep. You have a question?
So obviously there's a lot of different situations in poker. Like you can have different stack sizes, you can have different bet sizes. How constrained was this sort of model? Like how much could it generalize outside of like to like say 200 or 500 big blind?
For the 2-player and the 6-player bot that I just described, it was always playing either 200 big blinds fixed stacks or 100 big blinds fixed stacks. We developed later techniques that would be able to play arbitrary stack sizes. Yeah. Yep.
About test time compute, so if the model is larger, I assume it will take correspondingly longer at test time as well. So if you have a 100x model, 100x larger model, does it take 100x longer at test time?
For the models that we were using, no. But this was because we weren't using neural nets. So a lot of the computation was kind of like independent of the model size. Yeah.
I was wondering if like, given a certain test time budget, if you should just train a much, much, much larger model that uses up all of that time for inference at test time versus a smaller model that does search and planning and uses the same amount of test time?
That's a good question. So I think the issue is that at a certain point becomes like, so I think at some point it's probably worth it to do planning at test time rather than just training a bigger model. Because you can imagine that like, you know, training a bigger model, you have to keep like 10xing, you have to do some kind of multiple of the pre-training. And so at some point it becomes cheaper. If you imagine that you're only going to like do an inference once, like a call once to, let's say, like play against a world champion in Go or something, you don't, it's worth it to shift a lot of that computation to, like, it's worth it to 100x the computation at test time rather than 100x the pre-training.
Was your model optimized to be game theory optimal, or did you ever go into the exploitation part?
These poker bots were optimized to be game theory optimal. So we were trying to compute an equilibrium, and the idea was that, what we observed empirically was that by computing an equilibrium and playing that, we ended up doing very well against expert humans and beating them, even though we were not actively trying to exploit them. We never, I think a lot of people were interested in this question of how do you exploit expert players. We ended up developing techniques that could effectively do this in diplomacy by modeling the other humans that were playing, and I'll get to that a little bit later. We never actually applied this to poker, but if you're looking for an interesting research direction, I think applying these techniques to poker is something that, as far as I can tell, nobody's doing, and is definitely doable, I think, at this point. Okay, I want to move on to Go next. Okay, so this idea of doing search and planning is not unique to poker. And in fact, it's been widely used in games like chess and Go. And I think if you look at the performance in games like Go, you see a similar pattern, where I think most people underestimate just how much of a difference it makes. So here is a chart from the AlphaGo 0 paper. So AlphaGo is very famously this AI that beat Lee Sedol in Go in 2016. AlphaGo 0 is a follow-up that is even better and was trained with very little human knowledge. So you can see on the y-axis here we have ELO rating, which is a way of measuring the performance of humans in different models. And on the x-axis we have different versions of AlphaGo. So you can see AlphaGo Lee is the version that played against Lee Sedol, and it's just over the line of superhuman performance, around 3,600 ELO. AlphaGo 0 is the stronger version, which has an ELO rating of about 5,200, so clearly superhuman. But AlphaGo 0 is not just a raw neural net. It's a system that uses both a neural net and an algorithm called Monte Carlo tree search. And if you look at just the raw neural net of AlphaGo 0, the performance is only around 3,000. It's below top human performance. So I want to really emphasize this point, that if you look at just the raw neural net of AlphaGo 0, even though it was trained with Monte Carlo tree search, if you just run it at test time without Monte Carlo tree search, the performance is below top humans. And in fact, this was, AlphaGo was in 2016. It's now 2024, 8 years later. And still, nobody has trained a raw neural net that is superhuman in Go. Now, I noticed that when I mentioned this to people, they would say, like, well, surely you could just train a bigger model that would eventually be superhuman in Go. And the answer is, like, in principle, yes. But how much bigger would that model have to be to match the performance of AlphaGo 0? Well, there's a rule of thumb that increasing ELO by about 120 points requires either 2xing the model size in training or 2xing the amount of test time compute that you use. So if you follow this rule of thumb, if the raw policy net is 3,000 ELO, then to get to 5,200 ELO, you would need to scale the amount, the model size and training by 100,000x. Now, I want to caveat this. There's a big asterisk here, which is that I don't actually think AlphaGo 0 is 5,200 ELO. I think they measure that by playing against earlier versions of the same bot. And so there's a bias where it would do better against those because it's like trained through self-play. So it's trained against those bots. So I think the number is probably more like 1,000 to 10,000. But in either case, you would have to scale the model by a huge amount and the training by a huge amount to match the performance that you're getting by using Monte Carlo tree search, where the bot thinks for like 30 seconds before acting. And by the way, this is still assuming that you're using Monte Carlo tree search during training, during self-play. So if you were to take away the Monte Carlo tree search from the training process, this number would be astronomical. OK, so when I noticed this pattern, I started just like, whenever there was a domain that I was looking at, I noticed that a lot of people would think about how do you do deep RL, model-free deep RL, which was the cool thing to do in 2019. Less cool now, but still pretty cool. And instead, I would look at the domain and see how can we apply planning. And I think Hanabi is a really good, another example of this. And by the way, this whole talk is just going to be me going through different domains and talking about how planning has been like really, really effective. So Hanabi is this fully cooperative imperfect information game. And after AI became superhuman in poker and Go, people were looking for other domains that would be these new grand challenges. And in 2019, February 2019, DeepMind proposed Hanabi as this new benchmark. And they presented a new RL algorithm, a deep RL algorithm, that achieved a 58.6% win rate in Hanabi, which was very good, but not superhuman. Less than like 6 months, six months later, my teammates and I at FAIR presented a new algorithm that achieved a 75% win rate in two-player Hanabi, which is superhuman performance in this domain. And we did this using a surprisingly simple technique, which I'll get to in a second. And the key breakthrough was, again, we didn't do anything novel when it came to the RL. We just did search. And in particular, we did like basically the simplest form of search you could imagine. Basically, in Hanabi, there's uncertainty around like what state you're in, so you have this belief distribution over what states you could be in. And there's like 20 different actions that you could take in the game. And so we would just say, OK, for each of these different states that we could be in, there's either like play card 1, discard card 1, hint red. There's these different actions you can take. Let's just do a bunch of different rollouts to see if we were to take that action and then play according to our policy for the rest of the game, what would our expected value be? And we do like 1,000 rollouts. We get a good estimate of what our expected value is for each of those actions. And then we just pick the one that has the highest expected value. Here is what the performance is. If you just look, OK, let's set search aside for a second and look at the performance of like different pre-trained bots. So this is SmartBot. It's a heuristic handcrafted bot, and it wins about 25, maybe 28% of games. This is the algorithm introduced in the DeepMind paper, and it's a deep Q networks bot, and it got about 45% win rate. And this is there's like a whole sequence of papers on deep RL algorithms for Hanabi that would get increasing performance. This was, at the time of our publication, the latest one, which would score about 58%. This is what you would get by adding this search algorithm to the different bots. So if you take this handcrafted heuristic bot that was only getting 28%, and then added the simplest search imaginable, where you just like do a bunch of rollouts for all the different actions you could take, and then pick the one that had the highest expected value, that would boost your performance to nearly 60%, which was beating all the previous deep RL bots just out of the box. This was using like a single CPU core at test time for like a second. And the beautiful thing was that you could actually add this on top of all the other deep RL bots. So if you added it to like the latest and greatest bot, deep RL bot, you would boost the performance even further to around 72%. And then if you did this was only if you did search for a single player. So if you did it for both players, that's the green bars, and you can see the performance went up even more. Now I should also point out that the upper bound for this game is not 100%, because there are some like deal outs that you just cannot win. So really the top performance that's possible is like, I think maybe 90%. And so you can see like we're quickly saturating performance in this domain. Now, when my teammates and I at FAIR got this result, my teammate literally thought it was a bug, because it was just unimaginable that you do this like simple thing and the performance jumps up from like 28% to state-of-the-art 58%. And again, this I think is a trend that I've seen where people really underestimate the value of planning until they see it in the domain that they're working on. OK, any questions about this, or go? So we're not the only ones to notice this pattern. And in fact, there's this really great paper that was published in 2021. It just went on archive. Andy Jones is now at Anthropic. And he did a bunch of scaling laws for the game of Hex, basically using AlphaZero-like techniques. And he had this plot that I think was really fascinating. So on the x-axis here, we have the amount of compute that goes into training a Hex bot. Hex is this like board game that's kind of like a simpler version of Go. And this is the amount of test time compute that goes into the bot using the Monte Carlo tree search algorithm. And you can see there's like these ISO curves of different ELO performance. So if you want to get 1500 ELO in this game, you could either spend a lot of compute at test time, or you could spend a lot of compute at training time, or some combination. And he found that basically there's a trade-off between 10x of training compute is equivalent to 15x of test time compute. So what this means is that by increasing the amount of test time compute in this domain by 15x, you're getting the equivalent of increasing the training compute by 10x. Now, why does this matter? Well, if you're training a system that costs, let's say, like $1 billion, and you want to improve the performance further, you could either 10x that and go from $1 billion to $10 billion, or you could increase the inference cost from like a penny to 15 pennies. Now, for certain domains, you would prefer to increase the inference cost by 15x over increasing the pre-training cost by 10x. OK. Now, we've also worked on the domain of chess. And I think here, this is very interesting, because this isn't so much about getting top performance, but it's about imitating humans. So there was this paper, Maya, that came out in 2020. And what they were trying to do is, instead of just making like state-of-the-art chess bots, they were trying to make very human-like chess bots. And so they trained these chess bots on hundreds of millions of chess games from humans. And they created different models to match the ELO ratings of different kinds of, like different ELO ratings. And this was, at the time, state-of-the-art for predicting human moves in chess. Now, one thing that's really interesting about Maya is that for high ELO models, it was about 100 to 300 points, ELO points below the target ELO rating. So if you were to train it on 2,000 ELO rated humans, it would only be about 1,700 ELO. For the lower ELO ratings, this ended up not being a problem. For the higher ELO ratings, it was a challenge. Now, one hypothesis for why this is the case is that approximating human planning is hard for neural nets. That when you're at 2,000 ELO, your planning process is so sophisticated that it's actually quite difficult to distill that down into a neural net. And I think one piece of evidence for this is that there is one version of chess where there was no ELO gap for the Maya model, and that was bullet chess, where humans have very, very little time to plan ahead, and they just have to basically act on instinct. Now, what we found, we wrote a follow-up paper that was published at ICML 2022. And in this paper, we added planning on top of these supervised models. And so here's the performance that we get. Basically, we take, we pre-train on a bunch of human games, and then we add Monte Carlo tree search on top with different hyperparameters for the Monte Carlo tree search to regularize it towards the human policy. So this blue dot is if you just do imitation learning on human data. And the x-axis is accuracy of predicting human moves in different game states. And the y-axis is the win rate versus versus this blue model. So obviously it's a 50% win rate against itself. And then you can see the human prediction accuracy. It predicts about 53.2% of human moves in a test data set. And I should say this is for highly rated humans. If you add Monte Carlo tree search, you can see that the prediction accuracy goes up, and the win rate goes up. And this is, again, for different levels of regularization. So this is for if you regularize very closely to the human policy. And this is as you decrease the regularization, it moves further away. The prediction accuracy starts to go up, and then eventually it goes down quite a bit. But the performance keeps going up. So this kind of makes sense that as you completely ignore regularization towards the human policy, you have much more flexibility to improve your policy a lot, but the prediction accuracy goes down. But what's really interesting is that the prediction accuracy does initially go up by a pretty substantial amount. So roughly speaking, 1 percentage point increase in the prediction accuracy on this test set would correspond to a roughly 4x larger neural net and 4x more training data. And here we're increasing in both chess and Go by about 1.5 percentage points, or maybe 1 percentage point in Go. And what's interesting is that the optimal hyperparameter was the same for both. It looks like it's the same plot in both figures, but it's actually different. So I think this is really surprising because we're kind of taught that if you want to maximize prediction accuracy on on some kind of data set, the way to do it is to just take a giant model, feed that data in, train a giant neural net, and then see what it outputs. And here, that's not the case. If you add Monte Carlo tree search on top with the appropriate hyperparameter, then you're actually increasing the prediction accuracy by a substantial amount. And again, I think that's because you're adding this planning ability that the neural net is insufficient, is not good enough to approximate, that humans are doing. Okay, any questions? Yep.
I'm curious if you see similar gains using search in a space that's not in a game where there's maybe not a super defined optimal.
Yes, I'll get to that a little bit later.
Do you think the same scaling law of test time and training compute will hold in continuous domains where the states are not discrete?
I think it's possible. I think it depends on the domain and the technique, but it's possible. Yeah. Okay. So this idea of using planning to improve your ability to predict human moves. This is again a follow-up to the Maya work. So on the x-axis we have different ELO ratings, and these are levels, human ratings, ELO ratings. And on the x-axis, we have the prediction accuracy for predicting humans in those ELO ratings, in that ELO bucket. And you can see, let's just focus on this blue line here. So the circles is the raw Maya model. And the squares are the Maya model plus MCTS with this like tuned hyperparameter. And you can see if you use Maya to try to predict, let's say like, it was trained on 1900 ELO humans, and then we try to predict the moves of 1900 ELO humans. The prediction accuracy is only around 54%. If we then add MCTS, the prediction accuracy goes up by 2 percentage points. Okay, so we use this idea of trying to predict human moves better by adding planning to our AI for the game of diplomacy. So Cicero was an AI that we developed at FAIR that plays the natural language strategy game of diplomacy. And it was trained on 50,000 human games acquired through a partnership with webdiplomacy.net. And the performance was quite strong. I won't go through all the details of how Cicero, because again, this isn't a talk on Cicero specifically, but diplomacy is this very complicated natural language strategy game. We entered Cicero anonymously. I'll get to the results and I'll talk a little bit about examples of it. But we entered it anonymously in an online diplomacy league. And so first of all, kind of separate from the planning stuff, it was actually quite interesting that Cicero was not detected as an AI agent, even though it played 40 games of diplomacy, sending and receiving an average of 292 messages per game. And honestly, people were kind of shocked afterwards when we told the humans that, like, oh yeah, you have been playing with a bot the whole time. And we got a lot of messages like this. Fortunately, people were overall quite okay with the fact that they had been playing with a bot the whole time. We were pretty worried about that, but they seemed to take it quite well. As far as the performance, Cicero ended up placing in the top 10% of players and second of 19 players that played 5 or more games. And it more than doubled the average human score. Also, there was one player that mentioned post-game that, they thought that, they kind of joked that Cicero, the screen name that we used for Cicero was a bot, but they also accused a few other players of being bots. So I don't know if that was specific to Cicero, or maybe there were just other labs working on diplomacy that also submitted agents. Okay, so the way Cicero works, it takes as input the board state and the dialogue history of that, and it feeds that into a dialogue conditional action model. So this is a model that, again, takes as input the dialogue and the board state and tries to predict what all the players will do in the current turn. These actions are then fed into this planning engine. And again, I think this is one of the novel things about Cicero that you don't really see in a lot of language models today, that it would iterate on what it was predicting all the players would do and what they thought we would do. And it would refine these predictions by doing several loops, kind of like in a way similar to what we were doing in poker. And then that would lead to the action that we ended up playing, but it would also lead to these intents, these actions that we would condition our dialogue model on. So after we planned to figure out what moves we should do for this turn and what we thought other players would do for this turn, we would feed those plans into the dialogue model, condition our dialogue on those plans, and then output a message accordingly. And again, I think this is one of the underappreciated things about Cicero, that it wasn't like a typical language model where it was acting instantly. It was actually really expensive to run. We were using, dozens of GPUs, and it would take, sometimes at least 10 seconds for each message that it decided to send. But that time spent planning ended up making a huge difference for the performance of the bot. Okay, so there's a general trend here that for some problem, why does planning work in so many domains? And I think one of the fundamental reasons is that there's this thing that you might call the generator-verifier gap. Basically, in some problems, verifying a good solution is much easier than generating one. So for example, in poker, verifying that you're in an equilibrium is much easier than computing one. In chess, verifying that you're at a really good board state is much easier than finding the path to that very good board state. And in something like Sudoku, it's much easier to verify that you have a solution to a Sudoku puzzle than it is to find that solution. And this is true for domains like puzzles, math, programming, proofs, for example, it's much easier to verify a proof than it is to generate a proof. There are some domains where this isn't true. So for example, information retrieval, if I asked you what is the capital of Bhutan, I could give you 10 different options, and I don't think that would actually help you in telling me what the correct answer is, at least most of you. And also things like image recognition. These are domains where verifying isn't much easier than generating. And in these domains, we would expect planning to not make a very big difference. But when there is a generator verifier gap and we have a very good verifier, then we can spend more compute on the generation process and then verify when we've come up with a good solution. OK, so I've talked. Before I go to LLMs, do you have any questions so far? Because we got to talk about LLMs, of course, right? Yeah?
Would you say this is like another way to think about it is like the efficacy of forward search versus backward search from your goal? Or is that distinct?
I'm not sure what you mean by that.
So like you have a goal in mind and you're just searching backwards from from the goal to your current position rather than from an initial position to the goal.
There are forms of search that do both. And I think that's I don't think what I'm describing is assuming one or the other. I think you could do either one, depending on the domain. Yeah. OK, so we're going to talk about LLMs. I should mention, of course, that I'm only able to talk about published research, and so I'll keep this all of these discussions to things that are published. So what does scaling test-time compute look like in language models? There are instances of it, and again, I think people underestimate just how much of a difference those techniques make. So the simplest one is this algorithm called consensus. And the basic idea is instead of just generating one solution, you generate a bunch of solutions, and you take the one that's the most common. There was this paper, Minerva. So some of you might be familiar with what's called the math benchmark. So this is a benchmark. It's literally called math. And it involves many difficult math problems that are basically like high school, college level. People thought it would take a very long time to reach even 50% performance on this benchmark. But in 2022, Google published this paper, this bot called Minerva. And it got over 50% on the math benchmark. This was very surprising to the people in the LLM community, because math was viewed as one of these very difficult tasks that LLMs were really bad at. They did a lot of things to get the performance to 50%, but one of the things they used was consensus. So they generated a lot of solutions, and they just returned the most common one, and that actually boosted the performance of Minerva from 33.6% to 50.3% by generating 1,000 samples. Now, there are limitations to consensus. So for example, if it's really easy to do you could do consensus when you have a single number that you have to return as your answer. It's much harder to do consensus when you have to write a proof, for example, because you're not going to generate the same proof multiple times. But there are other things you could do. Another one is best of n. And the idea here is that you have a reward model that can score how good a generation is. And instead of returning the first one, you generate n solutions, and then you return the one the reward model considers to be the best. Now, with a good enough reward model, best of n beats consensus. But it is, in many cases, bottlenecked by the quality of the reward model. And in fact, if your reward model is not very good, then you will see this overfitting dynamic, which you kind of see here, where on the x-axis we have the number of solutions that you're generating, and on the y-axis we have the test time performance, the solution, the score. And you can see initially, as you generate more and more solutions and take the best one according to the reward model, it goes up, but then eventually it overfits and it goes down. So if you don't have a very good reward model, this can be worse than consensus. It is very useful in a domain where you have ground truth, chess is a good example where you've either won or you've lost, or Sudoku where, again, that you solved it or you haven't solved it. Can we do even better than these? Well, there was a paper that actually OpenAI published very recently. It went online about a year ago, but it was and that it was officially presented at iClear just a few weeks ago. This is called Let's Verify Step by Step, and they introduced this idea of process reward models. And the idea is that instead of verifying just the final solution, they're going to verify every single step individually. So yeah, they go through each of the steps, say, is it correct, is it incorrect? If it's incorrect, then they just mark that down as incorrect for the whole solution. Okay, so how does this compare? Well, okay, so in this plot, we have the number of solutions generated, going up to 1,000 or 2,000. And this is the success rate on the math benchmark. This gray line is consensus, also called majority voting. And you can see it goes up initially, but eventually it flattens out. But you can see it actually gives you a pretty big boost. So you're going from roughly 60% to almost 70% just by doing consensus. If you do best of n, you're getting an even bigger boost, and you're getting up to 72.4%. If you do this process reward models where you're verifying every single step with a really good reward model, you're getting an even bigger boost, and you're getting up to 78.2%. And you can see it still looks like that line would go up more if you generated more samples. There's some examples of this. I think this is a really interesting one in particular because this is a math problem. It's asking you to simplify tan of 100 degrees plus 4 times sine of 100 degrees. This, if you give it to the raw GPT-4 model, it would only get it right 1 in 1,000 times. But by going through the process of verifying every single step, you could generate 1,000 samples and then only take the one that the reward model says is correct, and your success rate would go up a ton on this problem. OK, I want to take a step back and talk about more broad, the broader picture about AI today. So I mentioned at the start of this talk, when I started grad school working on AI for poker, people felt like they had figured out the method for getting to superhuman performance in poker. There was this algorithm that we had, and it worked, and it was just a matter of scaling it up. And every year, the models would get bigger, train for longer on more data, and they would always beat the previous year's models. And that's very similar to, I think, the state of AI today. We have a technique that works, and we can train it on more data for longer with bigger models, and it keeps getting better. And there are some that say that that's all we need to do. But one thing that I want to point out is that the inference costs for these models are still quite low. You can go on ChatGPT right now, ask a question, you get a response basically instantly at very, very low cost. And it doesn't have to be that way. It wasn't that way for a lot of these games that we looked at. It might not have to be the case for language models as well. So the next goal, and the thing that I'm working on, is generality. Can we develop truly general ways of scaling inference compute? Now, this is a very difficult problem. We've developed a lot of these techniques, these search techniques that scale inference compute, but they've always been very specific to the domain that we've been looking at. And what I am working on, and others are working on, is developing very general ways of doing it. This would involve spending much higher compute at test time, but it would mean much more capable models. And I think for many domains, we're willing to make that trade-off. Yes, it's true that for ChatGPT, where you want a co-pilot for your coding tasks, maybe you don't want to spend 5 minutes waiting for a response. But there are many questions where we're willing to wait hours, days, even weeks for an answer. You can imagine that we would be willing to spend that kind of cost for something like a proof of the Riemann hypothesis, or for a new life-saving drug, or for the next Harry Potter novel. And I think very importantly, it can give us a sense of where things are going as we scale these models further. It can give us essentially a window into the future of what the state of AI will look like down the road as these models become even more capable. OK, so general advice for academics, because I know that a lot of academics, grad students in particular, are wondering how to do research in this new age of AI. And one thing I want to suggest is that planning is actually a relatively good domain for academic research. And I say relatively. I still think that it is much easier and better to do this kind of research in industry because look, the reality is you have way more resources in industry compared to academia. And it makes the research much easier to do. But I think compared to things like pre-training, planning is actually like a pretty good domain to work on in academia. And the reason is because if you think about the incentives of large companies, if you have a company that's serving billions of users, you're willing to spend a lot of compute upfront to train a really good model, but then you want the inference cost to be extremely low because you're doing potentially trillions of queries. And so the incentives are actually not in favor of planning. It's in favor of training a really, really, really giant pre-trained model and then having the inference cost be as low as possible.
Especially if you're giving those inferences away for free.
Yes. And so, like, if you're in academia, you don't really care about serving your model to trillions of users or billions of users. You just want to generate a proof of concept and like only generate potentially like a few samples enough to publish a paper and prove out an idea. So this is a domain where the balance isn't really as badly against you. I would also suggest, I mentioned for things like best of n, the bottleneck is really on the verifier, the quality of the reward model. You might want to consider working on a domain where you have an external verifier because then you avoid being bottlenecked by the quality of the reward model. OK, I want to close with this quote from the Bitter Lesson. If you haven't read this, I highly recommend reading it. I think it's a great essay. It's really short. And towards the end, he says, the biggest lesson that can be read from 70 years of AI research is that general methods that leverage computation are ultimately the most effective. The two methods that seem to scale arbitrarily in this way are search and learning. Now, I think when it comes to scaling learning, we have done a great job. And I think that bitter lesson has been internalized. I think there's more that can be done on the dimension of search. OK, so I'll stop there, and I'll take questions for the remaining time. Thanks. Yep.
What are your thoughts on the importance of undoing bad actions in this kind of generative AI applications where you're not playing against an opponent, and if downstream it turns out that you do a bad action, can you go back and undo it and do something else?
Yeah. So one of the things that I want to avoid doing is speculating about future techniques and what those might look like because I want to stick to like previously published work and very very broad discussions. So I think that might be a difficult question for me to answer. Yeah, you have a question?
These search algorithms that you've discussed in games like Go, are they time variable depending on the complexity of the game state, or is it always a fixed time cost?
They were anytime algorithms that you could spend as much compute for as long as you wanted, and you would get better performance the longer that you ran it.
I just mean that once you decide on that being a fixed time, would that fixed time kind of across the board want to play this game by hand?
When we did it for poker, we actually used a variable amount of time because we were targeting a certain number of iterations or a certain like solution quality. So it would think for variable amounts of time, but we didn't put a lot of time into optimizing that. Yeah. Yeah. Question?
The research that you described makes a very clear distinction between search and the model. And you're using the model inside the search as a subroutine in some sense. Mm-hmm. But when you look at something like transformers, there's a lot of research on this. And maybe they are doing some amount of research inside the model. And maybe, hopefully, by doing that, you can actually do better than just by having the model and search be separate things.
That's certainly possible. I think when I'm talking about search, really what I'm saying is scaling inference compute. I mean, search is one example of this, but I think that the bigger question is how do you scale inference compute to just be, and that could be with like some kind of external process, that could be within the architecture itself, where you can dynamically spend compute. There's a lot of different directions to pursue. So yeah, I definitely think it's like worth thinking more broadly than something like just MCTS or just like the algorithms that currently exist. Yep.
Coming again from more of a poker background, but one of the primary uses for these models is for humans to implement them in some way? And have you looked at all about like the implementability of these things? Like for instance, Nash equilibrium in the poker space can be incredibly complex, but oftentimes a lot of that's just noise. There's just, you have these preconditions that you put into it, and then you get all these very like small probabilities of doing this thing or that thing. Is there any sort of like human-facing takeaways that you've come from working on these models?
I think, like in terms of poker, I think it is very difficult for humans to do the kinds of computation that the bot ends up doing. I think that there were general takeaways, but it wasn't really about like the way that the bot approached planning. It was more about like the general strategy of the bot. So for example, like one of the things the bot loved to do was in very carefully chosen situations, it would bet huge amounts of money. So there would be situations where there's like $100 in the pot. Typically, humans would bet between like $50 and $100, and the bot would sometimes bet $20,000. And that was considered very, very unusual by humans at the time. They actually thought the bot, this is part of the reason why the betting markets were so against us, because they saw the bot doing these kinds of things, and they thought like this bot's a joke. It can't be good. But it turned out it ended up being very effective in certain spots, and so that's actually one of the things that the humans took away from the bot and started doing in their own games. Yep.
If I were to develop like a new search or planning algorithm, what are some like good qualities that would make this algorithm more scalable?
Some good qualities that make it more scalable. Well, I think you can really plot just like as you give it more compute, how does it do? And ideally, you would like to see that it continues to improve the more compute that you give it.
Please thank our speaker again.